Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm your host, Kristin Malavenda, the Communications Director for the school. In each episode, we dive into the groundbreaking research, bold ideas, and inspiring people shaping the future of engineering. Today, we're joined by Professor Saurabh Bagchi. He's an expert in making computer systems more dependable and secure. From cloud platforms to autonomous vehicles, his research helps keep the technologies we rely on running smoothly and safely, even in the face of failure or attack. We'll talk about what makes distributed systems so complex, how to secure autonomous devices, and what it takes to make machine learning systems more predictable. Saurabh, thanks so much for joining me today.
It's wonderful to be here.
So let's start at the beginning. Can you tell us a bit about your journey and what got you interested in engineering in general, and how did that lead you to the field of dependable and secure systems?
Sure. So, like many of our inspiration stories, mine also derives from a fantastic teacher that I had in high school. My high school was in South Point in Calcutta in India, and inspiring mathematics teacher in my 10th grade. The trouble was I also had an inspiring history teacher, and I loved history so much that I pretty much decided that I wanted to pursue humanities in college. But then my inspiring mathematics teacher said, no way, you have a flair for science and engineering. I want you to do science in your 11th and 12th grades. So I dutifully did that. I slogged through the preparation for the joint entrance exam, which is the exam for getting into the Indian Institutes of Technology.
Okay.
By far the hardest exam I've ever taken in my life. And I did well enough to get into computer science at the Indian Institute of Technology in Kharagpur. So that really started on my journey into engineering. Now, I also had inspiration from an early age from my father, who's a civil engineer. And he used to work for the Department of Telecommunications. And then he would build these buildings and microwave towers, which would bring connectivity to parts of the country which had never been connected. And I could see the kinds of impact engineers had through him. I traveled with him to many of these remote sites, and I would see the people, how they would benefit from getting connected, getting a telephone line. And that was very inspirational for me. So I knew that engineers, if they do their job right, can really have a huge impact on the society around them. And that really appealed to me. Now, you asked about dependable and secure systems. So that journey really started from my grad school when I had an offer for my PhD from the University of Illinois at Urbana-Champaign. My advisor, Professor Ravi Iyer, he calls me up at IIT one day and says that, how would you like to come and work in my group on this topic of dependable and secure systems? Now, I had never heard of this term dependable computing before,
Right.
So I cloaked my ignorance very well in that call. And then the RA offer came just 2 days before the grad school acceptance deadline of April 15th. So even though I had never heard of this term in my undergraduate, I just took this leap of faith because UIUC was a very well-ranked CS department. And so I decided to sign on to work in this topic, and that started my journey on this area of dependable and secure computing.
That's so interesting, and it's very interesting to hear how the various ways all our faculty members come to engineering and their area of study.
Right.
So when we talk about cloud services, we're all using cloud services every day without even thinking. It just happens, and we don't think about how it happens. So what makes these systems so complex behind the scenes? What don't we know about them?
Yeah, so whenever you go on Expedia and buy a ticket, you're using tens of applications which are running on the cloud. Whenever you go and purchase something from an electronic commerce retail site, then there are tens of applications which are again running on the cloud. So the whole objective of cloud computing, which it has been extremely successful in, is it hides all that complexity from the end users.
Right.
Now, in order to make this kind of seamless interaction work, the technologists really have had to build some very impressive pieces of technology. So when you have applications which run in the cloud, they have managed to satisfy three primary criteria.
Okay.
So the first one is, the buzzword for that is called elasticity. And a further buzzword there is infinite elasticity. So what that means is let's say that an ad runs in the Super Bowl and suddenly the demand for a particular kind of t-shirt shoots up. So now everybody starts hitting those stores in order to buy that. So suddenly you have a huge spike in the demand. So if you were running all of this in-house in computers here, you'd have to go in and buy more computers just to be able to handle the demand.
Right.
In the cloud, this all happens seamlessly where the demand is just satisfied. So this is what's called infinite elasticity, the ability for it to grow and shrink depending upon the demand. So some really cool technology has come around with virtual machines and containers in order to achieve this. The second one is the ability to handle failures. So computers are going to fail, but very, very rarely do you go to these cloud computing applications and find that they have failed and you're not able to use them. So again, there is technology there which is able to handle all these kinds of failures. Technical terms there are called failovers or failure containment and so on. So handling failures is the second of these three major things that have happened. And the third one is cloud computing is extremely economical, which is why the big cloud computing providers have huge margins for their services, margins of upwards of 50% profit margins. So you want to make these systems performing, so they need to be able to meet their latency requirements. When you go and send a request, you expect a response to come back within a fraction of a second.
Right.
But at the lowest possible resource expenditure. So you are allocating just the minimal amount of resources in order to achieve this. So these are the three big pieces why cloud computing has been successful, but also why really cool technologies have had to be developed.
So what are some of the common ways that these distributed systems can fail, and how is your research helping to prevent or recover from these failures, which are, as you say, are inevitable?
Yeah, so this is right in my wheelhouse where I work on how do you deal with failures of distributed systems. And these failures can happen in one of three broad ways. So the first way in which failures happen is because the hardware that we develop or the software that we write is imperfect. It's going to have bugs in it, so it's going to fail in unpredictable ways. These failures can happen because there's bugs in the software or because it's running on some platform which it was not meant for originally. Maybe it was running on a particular kind of hardware. Now the hardware gets upgraded and the software now does not have the right kinds of dependencies with this new hardware. The second reason why distributed systems fail is because of humans. So we as humans are imperfect creatures, so we are going to interact with these systems in weird ways. We're going to ask them weird things. We're going to send requests which were not anticipated. Maybe 10,000 people are going to jump onto a system and try to do something together so that'll lead to a load imbalance. So humans interacting with the system also lead to failures. And then the third category are bad actors. So these are these malicious security attacks. Now these security attacks can originate from outside of the system, external attacks, or they can originate through insider attacks as well. So these are malevolent actors who are deliberately trying to degrade the functionality of the system or bring down the system altogether, and as a result, distributed systems fail as well. So these are the three broad reasons why I have seen distributed systems fail. And in my own work, I've attacked how to prevent these failures. And if failures do happen, in any realistic system, you are going to occasionally have failures. How can you very quickly contain and recover from these failures?
Right. And so how does that research go? What are you doing? And I talked to another professor who does system verification. She was saying that they deliberately try to make things fail so they can figure out how to keep it from failing. Is that something that you do in your research as well?
Yeah, very much so. So this is, the technical term for that is called red teaming. So you have the red teams are those who are mimicking the bad actors and who are trying to bring down the system so that they uncover what are the vulnerabilities in these systems. So that's sort of a more empirical way of trying to improve the dependability. There are also more formal ways of doing it, like you mentioned, formal verification techniques, program analysis techniques. So our group has really distinguished itself in using data analytic techniques in order to improve the dependability and the security of systems. So what that means is that you observe the system's operation, you collect data from it, which anyway the system operators are collecting. You mine this data in order to understand what is correct behavior, what is incorrect behavior, and importantly, what are these breadcrumbs that are showing that the system is moving from correct states to an incorrect state. So you can stop that in midstream, and the system doesn't fail. So before our group and a couple other groups around the world, the predominant way of dealing with dependability and security was reactive. So once something happens, let's detect and let's do something about it.
Yeah.
Whereas we all know that a stitch in time is much better than trying to do things reactively. So this has been a major contribution of our work, is that we are able to see, using these data analytic techniques, as the system is progressing toward these dangerous, unsafe states, and is able to stop it and recover from that.
So in reading about your research, I came across the phrase graceful degradation. Can you explain what that means in layperson's terms, and why is it so important?
Yeah, so a very intuitive example of graceful degradation comes from something that we've all come across as we are driving. So this is where you have traffic lights which start blinking red.
Yeah.
So we all know what to do when such a thing happens. That's not the normal course of action. That slows things down, but it doesn't lead to accidents. So this is a very nice analogy for what graceful degradation is supposed to do. When you have a failure in your system, it should transition to a safe state. And in this safe state, all the bells and whistles of your system would not be available. It will not have the full functionality. Maybe your plane is going to fly consuming much more fuel than it originally was supposed to. Another example of graceful degradation comes from ships or boats, where they have electronic steering gear systems, and there is redundancy, and they have fail-safe mode built into it. So when this primary steering system fails, then they have mechanical linkages, which are completely independent of the electronic steering system. So they provide a manual means of steering your ship to safety.
Makes sense.
So that is really this notion of graceful degradation. Move to a safe state, so still preserve the security, the safety of the system, and then maybe on the side try to get back the system to the pristine, full functioning state as quickly as possible.
Oh, that makes sense. So you also work on securing autonomous systems, things like drones and self-driving cars. What kind of vulnerabilities do these systems face?
Yeah, so this is at the heart of the institute that we run, funded by the Army Research Lab. It's called A2I2, Assured Autonomy Innovation Institute. So in many parts of civilian as well as the military space, there is a move towards more and more autonomous operations. So we've already seen autonomous operations purely in the cyberspace. Now there is also a push toward making more autonomy in the cyber physical space, where these autonomous algorithms are going to direct troop movement. They're going to direct energy pipeline. So the cyber physical space. So when you look at doing autonomous operations in the cyber physical space, then the potential for things going wrong really gets magnified multiple fold. So in autonomous systems, you have various kinds of stochastic algorithms, in general terms, machine learning algorithms that are driving these different levels of autonomy. And you have different levels of autonomy from where it's just providing some assist to the human to fully autonomous operations. So the operations of these autonomous systems, to you and me, feel like they're not deterministic. For example, depending on the way an AI algorithm is trained, when a drone sees an obstacle of a certain size at a certain distance away, it may turn 45 degrees or it may turn 60 degrees. So to you and me, it seems like, why did it turn 45 degrees? Why didn't it turn 60 degrees? It depends on various factors like how this algorithm was trained, what kinds of data this algorithm was trained on. So this means that these autonomous systems have a certain degree of seeming non-determinism in their behavior. So now the challenge from the point of view of dependability and security is, when can you say that this behavior is still safe and secure?
Mm-hmm.
And when do you say that this behavior falls outside this envelope of safety and security, and therefore it's going to lead to something bad?
Gotcha.
Okay, so that's point number one. Now, a second order thing, a more advanced effect that we have to take care of in autonomous system operations is that what is bad is not immediately observable. So imagine that your autonomous algorithm is directing troop movement. So maybe the first 10 minutes of this troop movement nothing bad shows up, but then it's leading its way to a ditch.
Okay.
So then you know that looking forward, this is going to lead to something bad. So autonomous systems also have to take into account, safe and secure autonomous systems, take into account this look ahead feature, where I'm looking ahead and seeing that I'm not going to lead to a safe and unsafe or insecure state.
Right. So your work also spans embedded wireless networks. What are those, and where do people encounter them just in their everyday life?
Yeah, so embedded wireless systems, embedded wireless devices are all around us. So, so the number of embedded devices have exceeded the number of human beings on Earth several years back, 4 or 5 years back. And that gap is just increasing. So that just goes to show that the number of such devices has really been going through the roof. So as we come into this room with the key card, you have to flash your ID card,
Yeah.
and there is one embedded device in there, which is reading your ID card, doing some cryptographic operation, and so on. When you have an energy pipeline, which is transporting natural gas, let's say, then there are embedded devices all along that energy pipeline, which is monitoring the flow of the natural gas. So embedded devices are all around us. This laptop that I have, its storage controller has probably 4 or 5 embedded devices in there. Now, these have been with us for quite a while. One of the big things that's changed is that we have networked all of these embedded devices. So they all have different forms of network connectivity to them, which is great for many, many different purposes. And sitting here, I can look at what the gas pipeline status is.
Okay.
If the gas flow has slowed down, I can monitor it right from here. But this also increases vastly the attack surface for these kinds of embedded devices. So now sitting here, bad actors can be attacking these embedded devices, can make it such that they are communicating wrong monitored values to me. So you may think everything is going fine when it's going to blow up in the next minute. Right? So this is where the notion of embedded security really comes in. And this is front and center of the National Science Foundation Center that we just won called Chorus. So this, I believe, is the first NSF center from the Computing Directorate that Purdue is leading. And we are the lead, Purdue is the lead, and there are 3 other institutions which are a part of it. Georgia Tech, University of Southern California, and University of Wisconsin at Madison. And there are 6 of us from here at Purdue who are part of the center. I'm leading it. So the goal of this center is when you build critical infrastructure systems, be these energy systems, water transportation systems, and specific application area that we're focusing on is connected and autonomous transportation systems. So these critical infrastructure systems will have many, many embedded devices in there which are network connected. Now, because many of these are legacy systems, you cannot just wave a magic wand and say every part of the system would magically be made secure and reliable.
Yeah.
Because that would just cost you far too much money. You would have to bring down the system. So what you have to do is you have to make very strategic decisions about which parts of the system to make more dependable, more reliable, more secure, and make decisions about where to invest in these kinds of mechanisms. And so our center is in this has this goal of making connected and autonomous transportation systems more secure, more dependable by saying, okay, we need to put smart traffic lights here. We need to increase the level of wireless connectivity that is there in this region. So we would be able to make these kinds of strategic decisions how to make this overall system more dependable.
So it seems like in a lot of what you do, you need to balance the technical, economic, and human factors involved in all that. How do you do that? And is there a trade-off when you're trying to make something meet those factors? Are you giving up other things?
Yeah. So security is often a trade-off, and you have put your finger on that, is security involves making these kinds of strategic trade-offs. And the work that I've done in the past, along with a colleague from the economics department, as it turns out, on behavioral security, has shown what kinds of human biases, human flaws come into the play when we are making decisions about security investments. So a very simple one is, but a very powerful one is, we often tend to overestimate some low probability events and underestimate some high probability events.
Okay.
So we all go around driving with one hand as we are talking on the phone with the other. Definitely don't do that because we think, oh, bad things happen to other people, not to us.
Yeah.
So that's an example where we are underestimating some fairly likely event if you do this kind of unsafe behavior. And there are people who would say, okay, I'm not going to fly in aircrafts made by this particular company because of some bad news that I've heard. Right? That is a very low probability event. So this also we found through doing human studies comes into play when people are making decisions about where to invest in the security. Another one is we've been all taught don't put all your eggs in one basket.
Right.
So there is a spreading heuristic. So if I have a connected system, an autonomous connected system, let's say, and there are 100 assets in there. So then the natural human tendency is to put a little bit of my security investment in all 100 of these.
Right.
Whereas what we have shown through our work is if you could analyze the system, you'd identify which are the critical points. So if that critical point goes down, then your whole system is toast. So you really should put more of your assets on those critical points. So we are going to have these biases. Our work has shown how you can help people understand the impact of these biases. And then in subsequent work, what we've done is the government, by putting certain kinds of incentives, can try to correct some of these biases. So for example, our work was taken up by a federal regulatory agency, for energy regulatory agency, and then there are this notion of cyber insurance, which cites our work because we showed that this is an example of an incentive that you could provide in order to correct some of these biases.
So when you work on something for so long, how do you keep your kind of passion and motivation for it, decades into your research?
Yeah, I think that's a fairly simple answer. Is we are very fortunate to be surrounded by really motivated students, energetic students. So we have a constant stream of students coming through. And my lab is a fairly large lab, and I'm very fortunate to have just fantastic students in there. They bring fresh ideas, they bring their enthusiasm, they keep us young.
I'm wondering too, you mentioned your teacher who directed you towards engineering, and I'm sure you had plenty of mentorship along the way. How do you view your role with your students in terms of mentorship? How does that work?
Yeah, so here I'm powerfully drawn to a mentor I had in my graduate school. My advisor, Ravi, was a fantastic mentor. He really showed me the passion that you bring to technology and the impact that this technology can have. How do you build reliable systems? So around that time, or a little bit before that, there was this incident called Therac, where a cancer radiation therapy went really bad, not because of a mechanical failure, but because of a software race condition. So we really learned how to analyze this, and this gave me this idea that this has implications outside of your ivory tower, whether how you build your systems. And I've had the good fortune of building systems which are widely used today by many commercial vendors. So for example, we found a vulnerability in smart TVs, which would have let anybody come in and hijack your smart TV and all of the credentials that are in there.
Oh, wow.
And then now pretty much any smart TV which is out there has this vulnerability plugged with the software that we developed. Another one was with smart watches. Again, maybe not as life critical, but if you are relying on your watch to measure your heart rate and somebody comes from outside and just tampers with it, then that's bad. And so again, we were able to discover the vulnerability, report it to the vendor, had it fixed, and now that's running everywhere. Another example comes to mind from my grad school days is where a Mars rover had been sent and it was up there in Mars, traveling on the surface of Mars. And then it stopped responding suddenly.
Okay.
And then this was because of a bug in the real-time software that was running on that rover. And Mars is like 200 million miles away. So just 150 million miles away. So just imagine having to do a debugging 150 million miles away over a really low bandwidth wireless network link. And somebody I had as a professor at Illinois, Professor Louis Shah, who then became a fantastic mentor to me, he was part of the team that did this kind of debugging. So these were really inspirational stories, and I have been fortunate enough now to be the author of some of these stories in my career as a researcher. So I think this notion of building dependable and secure systems is very real to me, and it impacts people's lives.
That's what I think is so cool about what you do in particular, is just that, you know, if you're walking down the street, people are using smartphones and watches and watching smart TVs and using distributed systems, and they don't necessarily know that you've done this work, but you can see the impact of it just in everyday.
That's right.
In everyday life.
That's right.
What do you look for in a student? You mentioned you have lots of students that work with you. When you're considering whether or not to take on a student in your research group, what qualities do you look in that person that makes you think that they'll be successful at your brand of engineering and research?
Yeah, so I spend a lot of time interacting with students before I hired them to work in my center or in my institute. And I've been very, very successful and very fortunate to have really the top of the line students. But that has been a very conscious decision with the amount of time that I spend vetting them out beforehand. So at an abstract level, what I look for is a certain degree of passion in the field that they're getting into. So a very simple question, maybe I shouldn't give out these simple questions, these litmus test questions, but I do see what they have done outside of their coursework, outside of what they were really required to do. And that is a very telling example. And then, of course, I give them various kinds of quizzes. I have them do a little bit of work with me at times before I get them on to our group. And that tells me how well they'll be able to do. Plus, I have now built up these networks with various universities in the US as well as outside, where in some cases I'm working with them on their senior thesis along with their advisors in their home institution. And that is very telling as to how they're going to shape up in my group.
Gotcha.
And these days, if they have offers from us as well as many of our peer institutions, you name them, Georgia Tech, UT Austin, Illinois of the world, they are likely to come to me because I have this comfort factor with them and they have that comfort factor with me.
Yeah.
With Illinois, I can't say too many bad things about it, but with the others, I know what to tell them, drive them to Purdue.
To come to Purdue. Well, it doesn't sound like you have any free time, honestly, but outside of research and teaching, what do you do to enjoy your free time or to relax, maybe?
Yeah, so I love traveling to the less traveled parts of the world with my family, and then and thankfully our job gives us a lot of opportunities for travel, which I love. And whenever I go to a conference, I'll carve out a little bit of time to also see the place around there and go off the beaten path as far as I can. And I love writing about these travels as well. So I write a blog post which has been carried by communications of the ACM, Scientific American, and The Conversation, where some of these are technical ones and some of these are about these off the beaten path travels that I've had. So that really is a good source of sustenance for me. And what I just mentioned is writing also helps me clear out my brain and makes me think deeply about things that I care about. So this is like writing not just papers, but writing for a more general audience.
Gotcha.
And then I love running and biking in West Lafayette trails with my wife, and then I'm a fairly avid player of badminton and tennis. So I have a good group that I play with, and students in my group now joke that has now become a criteria for to be hired into my group, is that you have to have an interest in one of these sports that we play regularly. I
think I saw you once playing pickleball at a local gym too, so that's become very popular as well. You talked about how you got some of your passion for engineering by observing what your father did in his career. Do you make a point of kind of bringing your children along and showing them the impact of your work to get them interested in it?
Yeah, our son is sold that he wants to be a computer scientist. We'll see once he goes through the rebellious teenage years how far that will persist. But right now he seems to be sold on being a computer scientist.
Well,
I tell him it's a hard to get in there,
yeah.
but if you can, it's a profession that'll reward you many, many times over.
Absolutely. Well, Saurabh, thanks so much for taking the time to talk to me today.
It's been a wonderful conversation.
That's it for this episode of Engineering Innovations. If you enjoyed this conversation as much as I did, you be sure to follow or subscribe wherever you get your podcasts and check out more episodes on our website at purdue.edu/ECE/podcast. You can find that link in our show notes. And help us spread the word about the podcast. Share this episode on social media and tag us. We'd love to hear what stood out to you. You can find links to our social media platforms and all sorts of things. I'll post a link to your blog too, if you'd like me to, in the show notes, so people can get an idea of your writing. So until next time, I'm Kristin Malavenda. This has been Engineering Innovations, and I'll be back next month with another new episode.